1, live. Hi, everybody. Welcome to the Frosty Drew Observatory and Science Center's Stargazing Nights live event. Tonight, as it's been for quite a bit this year, we are under some clouds, and we are expecting showers and a potential for T-storms tonight, all of which will likely keep us from being able to show you any live views through the telescope tonight. Now, we've had a clear bout of weather last week, and it was really fabulous, and myself and some of our other astronomers were able to get out and do a lot of really great data collection. And we're going to be showing you some of this data, some of these images, and we're going to be talking a little bit about what we're showing you and a little bit about what's going on in space right now. But first, I just want to say, we're really happy that you're joining us, and we've been doing this now for a couple months, and I feel like we're doing pretty good. And we're getting a lot of great feedback from you guys, and we're having a lot of fun doing it. Now, tonight it's a little hot, and we haven't put our air conditioner in yet, so if I start glowing, that's just my awesomeness radiating, right? So on tonight's session, we have two astronomers. We have Derek Schott from Connecticut, and we have myself coming at you from Providence, Rhode Island. And we have two moderators tonight. We have Jessica, who is also coming at you from Providence, and we have Brian Kelly coming at you from Braintree, Massachusetts. But Brian dropped his microphone into his bowl of soup, so it's not working. So we're going to see Brian kind of popping in and out, and he just might be silent tonight. We'll see how that works out. Regardless, it should be a good night. Now, I also want to do a quick shout out to everyone who's been donating. I mean, you guys are really helping us out. Our on-season, or our big summer stargazing night season, which is really important for us, usually kickstarts on Memorial Day weekend, which was last weekend. And this would have been our second week in doing that program. And that's a really big time for us at Frosty Drew. It's a time for us to raise a lot of money that helps us get through some of the quieter parts of the year. Now, considering that it's cloudy with showers and thunderstorms tonight, we wouldn't have opened anyway. So this is better than what we would have been on site, where we would have just been in the Sky Theater talking largely to ourselves. So you guys that are donating, you're awesome. Thank you so much. We totally appreciate it. Now, a couple weeks ago, we started a process of having you guys write in during the week with questions you may have that you would like addressed on the live chat, a live presentation. And if you have those questions, you can always submit them to astronomer@frostydrew.org, and we'll get to them next week. Now, if you have a question tonight during the session, don't submit it to astronomer@frostydrew.org. Instead, just type it into the chat right on the right-hand side of your screen there. That chat is where we have discussions that are going on. You can talk amongst yourselves, and you can also talk with our moderators. If you have questions you would like us to pose over the air, present them to our moderators over the chat, and then they'll read them off live over the air for us to answer. Now, I'm going to go over a few questions that we've had this past week. So the first question came in from Maria Bulmetis. She asked, is Comet Swan still visible? If so, how do I see it? Okay, Maria, Comet Swan. Comet Swan was becoming amazing. This comet went through some really great outbursts. It reached its perihelion is pretty much, I think it's going to be either today or within the next 2 days. And we got really excited about it, but there was an addendum. There was a caveat there. And that caveat was that with all of these outbursts that have been happening on the comet, outbursts are when that nucleus of the comet, the actual rocky part of the comet or the icy part fractures, and a lot more volatile material becomes exposed to the solar wind, which causes it to get substantially brighter. With all these outbursts we've experienced, we were speculating that what happened with Comet Atlas might actually happen with Comet Swan, where it will kind of die down. I have a picture in here of Comet Swan real quick that I could try to throw up for you from the last time we really got a good view of it. And here we go. Now, this isn't an image that we had captured. This is an image that was captured by probably one of the best astrophotographers on the planet. And his name is Damian Peach. And he captured this from Chile. Now, this here was Comet Swan when it was rocking socks. Unfortunately, Comet Swan is doing what we thought it would possibly do. It has started to fade. And it's because of the outgassing. A lot of the comet's volatile materials are burning out quite quickly, and it's fizzling out. Comet Swan became naked eye visible for a pretty good period of time. When this picture was taken, it was naked eye visible. Though since then, Comet Swan has dropped way below naked eye visibility, and it is now getting to a point where you can't even see it in binoculars anymore, sadly enough. So you're going to want to kind of get, sadly enough, you want to get Comet Swan out of your mind, right? I mean, when you look at this image here, I mean, you got some really great stuff in here. I mean, here's you see like the dust tail on the comet, the ion tail here. This green area this is a comet's coma, which is an atmosphere that forms around its nucleus. And all of these, when you look along the tail here, you see like this little anomaly right here. You see another little ripple right here. And then if you come down here even further, you have this wavy part here and all this bunching up of matter in the tail. This is called tail disconnects. And what happens is usually there's an event on the sun, like something like a coronal mass ejection, where you get a little bit more magnetism, a little bit more plasma that blasts into the solar wind. And when it hits the comet, it just strips the tail right off the comet and a new tail forms. And this happens quite frequently with comets like this. So before I go on too much about Comet Swan is unfortunately no longer a hot target. But we do have a new one, Comet C 2019 U6 Lemon. And Comet Lemon, which is currently in the constellation Canis Major, may follow the same path that Comet Atlas and Comet Swan followed and brighten up nicely. It's already gone through a couple outbursts. So we'll have to give it a little bit of time, see where it goes. And we may still yet get our naked eye comet in the north. So the Southern Hemisphere, they always get the great comets. Northern Hemisphere, not so much. So we had another question too. This question is from Ken Sebesta. Ken has been joining us almost every week, and we are totally all about it. It's very, very awesome that he has been.
And Ken is with us again tonight.
Way to go, Ken. So you asked last week, is there a video available for tonight's show? Ken, that's a really great question, and I don't believe we've really been covering that on the broadcast. So yeah, that's Brian with his soupy microphone. He dropped it in his soup. Yeah. Go, Brian.
Hear now.
So,
we can hear you, though, Brian.
So. Oh, is it working?
Yeah.
Wow, amazing.
Can you hear me?
We got
you. We can hear you, but you can't hear us.
I can't hear you, but I can hear me.
All right.
Oh, well.
There we go.
So our videos, every time we broadcast like this, there goes Brian, he just left. Every time we broadcast like this, we archive the videos to our YouTube channel immediately for you guys to be able to view. And they stay up there, and they're going to stay up there, even when the world is back to normal and we forget about all this. So at any time you want to check out any of our archived videos or live streams, just check out our YouTube channel. You can either go to frostydrew.org, and in the top right of any page, you'll see a YouTube icon. That will take you to our YouTube page. Otherwise, you could just go to YouTube and search for Frosty Drew Observatory and Science Center, and that will take you to our YouTube channel where you can find our previous videos. So thanks for asking that, Ken, and we should be covering that more often. We have another question from Paul C. Can you tell me when is the best time for Milky Way photos? I am thinking of around June 20th. Could you also tell me where is the best spot for Milky Way photos and parking? All right, so Paul, best time of the year, hands down, right now. Springtime in New England gives us the best view of the Milky Way, but if you don't want to swing the morning hours to catch a good view in a shot, then you could set up in June or July, right after sunset, and get a view. We will have the Milky Way in our sky, largely from April all the way through early September, though the prime season for Milky Way is definitely April and May and most of June. Now, best spot for Milky Way photos, Frosty Drew, guys. I mean, come on, darkest spot in southern New England. I mean, if you've been there, if you've seen it, you know that it's the spot to be. And as of last Saturday, Ninigret Park, which is home to Frosty Drew Observatory, has been reopened to public access. Yay! Awesome. That doesn't mean that we can just bombard the park and give everyone high fives and big hugs and get into huge groups looking at the Milky Way, because then you're just going to close the park down again, right? So we want to make sure we're following the regulations in the state. No out-of-state visitors for now. Just how it is. I don't make the rules. I just repeat them. Social distancing, keep 6 feet apart from each other if you're out. This doesn't apply to families and households, but don't be out there with your college alumni having a party, right? So, and parking in Ninigret Park. I mean, if you can't find parking in Ninigret Park, then you have no business photographing the Milky Way. So, Dean Patterson had asked, just writing to inquire if I stopped in one evening in the parking lot to take photos, not on a public night, is that acceptable, or is the lot closed and or that area? Dean, so I think I pretty much answered your question with the last statement. Yes, you can visit the park on nights that Frosty Drew is not open. You can also visit the Frosty Drew campus. Now, the Frosty Drew campus will often have our astronomers working, and they will greet you. They'll let you know that they're closed, but they won't chase you off. The only circumstance where you may get chased off is if we are hosting a private event. We often host private events at Frosty Drew Observatory. We're not doing them at this moment because of the current lockdown, but we will be again once everything eases up. And private events come with the exclusivity of the campus. So we'll hang a sign out that says, "Thou shalt not pass, private event." If you see that sign, do not enter the campus or you will be chased off. Otherwise, you can come and visit as long as you adhere to some basic requirements. Don't put trash on the ground. Close the gates you open. Don't disturb anyone that's there, so no white lights. And be cool. Take out what you bring in. A lot of times we get down there during the next night, we see, liquor bottles and beer bottles and candy wrappers and the gates open, and it's just a mess. Respect the park, respect the wildlife refuge, and we're totally cool with it. But you won't have power and you won't have facility access either. Michael Aiello asked, I wanted to purchase a telescope for my son who is 9, and I have a reasonable budget, hoping to get something he can grow into where we can observe various objects, including Jupiter, Saturn, Mars, etc. Michael, excellent question. And this is a question we get quite frequently at Frosty Drew. So we have a telescope that we recommend to just about everyone who asks. And it is the Orion XT8 Classic Dobsonian. This telescope is pretty much the sweet spot for just about everything, for price, for portability, for ease of use and setup, and for objects that you can observe with it. It costs about $400, and you get it from Orion, so telescopes.com. You're not going to get it in an department store. And this telescope is excellent. No matter what you do down the road, if you stick with astronomy, you become an astronomer, you become an astrophotographer, no matter where you go with your gear, you're always going to have that XT8 with you, and you're going to drag it along, and you're going to look through it while you're doing everything else with your professional rig. Every time we set up our telescopes to do imaging, I always drag out that old XT8 and take a look through it and observe the sky. And Derek will tell you the same thing.
One of the ones we use at Frosty Drew in the yard on our public nights. The Dobsonian design is great because it is just a very simple mount that you can just point anywhere in the sky and take a look and see what's there. You don't have to worry about electronics. You don't have to worry about computers. You don't have to worry about anything.
You don't have to worry about alignments. Nice and easy.
Look through the finder scope and line up on the target you want to go for.
And if you guys have visited Frosty Drew, you've probably seen Derek or Unity, our young team member, operating that telescope. And the things you can see in it are quite amazing. It'll show you the entire Messier catalog, most of the NGC catalog, all the planets, and it would be, it's really just a fantastic telescope to use. I'm writing right now.
The 8-inch looks too big for you. There is a 6-inch version that is also quite a good telescope.
Okay, so that's all the questions that we've gotten this week. And we get a lot of, so there is a question that we do keep getting. It's about visiting the observatory. I'm going to take a quick moment to talk about that. I don't want to be talking all night without showing you guys awesome stuff. But the observatory, so right now we're working on our plan for reopening. Phase 2 of reopening Rhode Island begins on Monday, June 1st, and that is going to be a very important day for us because it's pretty much is going to allow us to start opening up. Now, we have a lot of things are working out. We have to figure out better flow dynamics, get our paperwork in place, and figure out how we could minimize the amount of people on campus. But we are trying to target a date of June 5th to reopen. Now, that is the earliest date we're targeting. It doesn't mean we're going to get that date, but we're going to try for it. Unfortunately, out of the door, there's going to be some regulations. Number one, the first few weeks that we're open, we're only going to be accepting visitors from in-state Rhode Island. We're going to talk about how we might be able to work around that, and really depends on the state of executive orders in Rhode Island, what the regulations are stating. And if out-of-state visitors don't have to quarantine anymore, then we will lift that. We're also going to be limiting the amount of people on the campus at any given time, so we're going to be integrating a ticketing system, which means that you're going to need a ticket to get yourself into a time slot. You're going to be able to find a lot of information about this on our website, frostydrew.org, and on the top, right underneath the header, you're going to see an area that says, our statement regarding, COVID-19 and SARS-CoV-2. And on that page is where you're going to get the most updated information about what our plans are and what we're doing. Our ticketing system is not going to be permanent. This is a temporary addition until we all get through this. So, and I'm going to say one more thing real quick. And this is probably the most important thing I'm going to say about its reopening is Frosty Drew will not tolerate any discrimination in regards to this virus at all. And it's important to note that if you're incapable of keeping your views to yourself about how other people are conducting themselves, then don't visit until you can, because we don't want any of that on our campus. This is an escape from current situations. This is an escape from people's daily lives. This is a place where we can look at the stars and we can find solace. So we don't want arguments. We don't want a lot of that. So
this kind of leads into a question that Kerfway had. She's asked, what inspired you to do what you do? With the kind of knowledge that you have about astro, does it impact the way you view what life is?
Oh, what do you think, Derek?
Why do I do this? I think I do this because when I look up at the sky, I feel small. And it is looking into a wealth of information that we can see, but it takes time, effort, and energy to build an understanding of what's going on above our heads. And those skills can be used in everyday life to bring back down to earth and say, I've got this situation and this is how, we deal with it. Or I've got this event and this is, how we go through it. But it's something that, it's nice to be able to just look up and say, I wonder what that is tonight. And then start looking and then looking some more.
So, yeah, the same thing with me. I mean, what got me into it was Star Trek, because Star Trek is just awesome. But it's more than just that. I mean, for me, that whole Carl Sagan's pale blue dot, when we had Voyager fly way past Neptune, we're talking almost as far as Pluto, and it turned around and it took a picture of the Earth, and then Carl Sagan gave that really awesome commentary. I was in high school and that happened, and that commentary really, it rocked my world. It changed my point of view of just about everything I believed in. And because of that, I couldn't get it out of my mind. But from a perspective of life, yeah, absolutely. So like Derek was saying, you're looking at things and you feel small, and it's easy to feel that way. But you got to look at, so one of the things we try to do at Frosty Drew Observatory is introduce you guys to what we call in astronomy a cosmic perspective. It's the idea that humans are not living on Earth, but we're part of Earth. You know, we're just as much part of Earth as the trees and everything else here are. We can't leave Earth the same way you can't take your leg off to go to work. And Earth and us are also part of the sun and the solar system, which is the sun's system. And even more so that we're part of the universe. Just as much as we're in the universe is in us. So you can look at things from a perspective of, 200 billion stars in the Milky Way, and that from, the Earth just to the sun is 8.5 light minutes. From the Earth to the center of the galaxy is 25,000 light years. And from the center of the galaxy to the other end of the galaxy is another 50,000 light years. And this galaxy is not even that big. There are trillions of galaxies out there, a lot of them that are way bigger than this, with the visible universe spanning about 90 billion light years. Now, yeah, that can make you feel really small. But if you look at it from a cosmic perspective, there's a different way you can feel. The idea that all of those atoms that are in our bodies, all the atoms that are here on Earth, all the atoms that we see with everything that we see, our friends, our family, our children, our toys, our video games, all these atoms, they formed in the stars out there, those high mass stars that exploded as supernovas, and they spread all of their atoms across the galaxy. And we're borrowing some of those atoms right now to live. And we have the same stuff in us as in everything else, hydrogen and carbon and oxygen, and we have nitrogen is the primary constituent in our atmosphere. I mean, it's the same stuff everywhere. And that is evidence that we are part of the universe, not living in it. And that is amazing, because of all of that distance that I said before, that 90 billion light year visible universe, this is the only place we know of where the universe falls in love with itself, where the universe can talk to itself about itself, where the universe is aware of itself. All those atoms in your eye that enable you to see the universe is the universe looking back at itself. And that makes me feel big. So let's move. If no one's got anything else to say about that, I'm going to show you something real quick from an app, a star charting app, because I don't actually have a picture of it here. And this star, so this is the constellation Cassiopeia right here. And I don't have my screen settings set to something that would look really awesome at night, or from like a position of just looking at the sky. So it's going to look kind of messy. But the W would go like this. This little star right here, this star is called Eta Cassiopeia. It's also known as Ackerd. The star is roughly 19 light years distant. And this star is the same size, the same brightness, and the same temperature, so the same color as the sun. And when you look at this in the sky, it's really quite dim. It's easily overlooked, especially if you're in the city. But that's what we look like, from 18 to 19 light years distant. And when I'm having a bad day, and I feel like the whole world's coming down on me, I'll step outside at night and I'll take a look at that star in Cassiopeia, and I'll remind myself that my problem is smaller than that star. So the next time you're out, take a look at the W. You get your W in Cassiopeia. The star, so from the center of the W down towards the right, the star in the middle that's just slightly off the line is also known as Ackerd, Eta Cassiopeia. So I'm going to show you guys real quick.
It's also a star that we show a lot in the telescopes at Frosty Drew.
It is. It actually, that's right. It has a little binary star with it too, like most stars out there.
Yep.
All right. I'm going to put up real quick a video that we captured on the 27th of Venus. Now, if you guys have been tuning in, you know that I've been capturing a lot of Venus data over the last couple weeks. And this has, I'm charting its progress as it moves towards what we call inferior conjunction. Now, inferior conjunction happens when Venus orbits in between the Earth and the Sun. And up until that point, we see Venus during its waning phases. And I've started cataloging Venus's changes when it was still in its waning gibbous phase. And I've been charting it almost every day as it goes down towards its crescent phase and into inferior conjunction. On Thursday, when I captured this video, Venus was at a 2% waning crescent. And you can see in the video here just how small Venus's crescent is getting, but Venus's size is getting substantially larger. So after this image was compiled, this is what it looks like. Hang on one second. Bring this up real fast. And let's see here. Venus is, there's definitely something else to note about this too. That not only, when you're looking at Venus, I'm capturing these images during the daytime, you know, this data. And in doing so, it gets a little dangerous as you start approaching that last few days before inferior conjunction, or last couple of weeks, because you're getting closer and closer to the sun. So this here is a composite of that image. You can see the super thin crescent, and you can see some of the blues and some of the greens in here. What you're looking at are just barely visible features of the clouds over Venus. Now, when you're doing this kind of stuff, I've gotten to the point now where on the telescope I'm using, there's a corrector plate, it's a lens in the front, and it's pretty big, and we're talking 10 inches of diameter. I can see the reflection of the sun off the primary mirror on the corrector plate. Now, in the middle of the corrector plate is the secondary mirror. And I've been tracking every day the progress of that reflection of the sun on the corrector plate. Because once it reaches the outer diameter of the secondary mirror, I can't do any more work, because that means the sun is going through the telescope's optics. And if I put my eye on, it'll burn my eye right out of my face. If I put the telescope or camera on, I'll burn the camera right up, and it will ruin the telescope. And interestingly enough, when I was outside with Jessica the other day, when I captured this image, I was taking the dust cap off of the corrector, because I don't want to move the telescope with it off, because I might accidentally look at the sun. And my hand, I don't know if you could see it on the camera, but right here got into the light from the reflected sunlight, and it burned me instantly. Now, that's how hot it is. And that's just coming off the first mirror. That's still not completely concentrated light. So I feel like I'm fighting the good fight here. You know, I'm taking on the dangerous astronomer, right? Don't want to blast my eye out of my face. And now I'm going to show you real quick another image here that we've been showing weekly as well. And this is the progression of Venus over the last couple months. Now, if you look over here on the right, you can see you have Venus here is just after third quarter. Venus has just dropped into its waning crescent stage. This is April 6th. But then as we continue, you notice that not only is Venus getting thinner, but it's getting substantially larger. And this is what you're seeing here is the truth. It's not that I'm changing my camera or magnifying the view more. It's not that I'm cropping the images so that it's actually bigger. I'm using all the same equipment. And these changes in size you're seeing, this is called angular size. It's because of Venus orbiting closer to us as it moves towards the spot of inferior conjunction. Now, we've had a couple of days of clouds, and it's going to continue, but tomorrow afternoon, it might clear long enough for me to try to get out there and, you know, do the daredevil thing again, try to avoid the sun and see if I can get another image. Now, if I'm careful enough, I may be able to track Venus all the way through inferior conjunction, because it isn't going to go, it's not going to cover the sun. That would be considered a transit of Venus, and we're not going to see that happen until 2117. I'll miss it. So everyone on this, on our live feed's going to miss it. I don't know about you guys, but that's pretty far off. But I'm going to try to chart it through that period. And you also notice, if you take a look at sunset in the eastern sky right now, or the western sky, you've noticed that Venus is setting earlier and earlier and becoming harder to see. That's because it's getting close to the sun. Give it a couple more, give about another month. We'll be seeing it clearly in the morning sky. And Venus will become the morning star. So
I've got a picture of those if we want to show those real quick.
do it.
All right.
Absolutely.
So earlier in the week, I went out and took some pictures of Venus, kind of as a landscape type thing. So let's see. I think this is the right window. So I showed this earlier as well. This was taken on the 21st. You can see Venus here, and then you can see just below it is the planet Mercury. The two together, that was a conjunction that happened earlier in, I guess, last week now. What is today? 27th. So a little under about, I think that was Saturday. So what's happening here is you've got just the way that where we are on Earth observing both the planet Mercury and Venus puts them close together in our sky. They're still quite far apart. Mercury takes about 88 days to go around the sun, and Venus is around 265, no, 280. Oh, I'm going to draw a blank and have to look that one up again.
224.5 days.
Is it that short? I thought it was, wow, all right. So yeah, that takes about 3 times longer than Venus to go around the sun, or than Mercury. So this was the 21st. You can see they're quite close together. And then a couple days later on the 24th, we've got the moon in the picture now, because the moon has moved from right to left across the sky and become a crescent. In the picture on the 21st, it was a new moon. Venus has moved quite a bit closer to the sun. You can see it down here on the left, and Mercury, by and large, hasn't moved a lot in the sky. It's only moved, 3 days worth, and it's I think it's on the far side of the sun right now, or farther away from us. So it's kind of in the gibbous phase, and which means it's moving towards the left in the image, whereas the moon is also moving towards the left, and Venus is moving towards the right quite rapidly. Because if you think Venus was up here 3 days ago, that's quite a bit of sky to cover. And these were shot with the same lens, slightly different, perspective and just angle of shot. But you can see the same, sports field lights in the bottom there. And this one was taken a little bit earlier in the evening. It got cloudy right after I took this picture, so I couldn't wait as long to get the nice dark sky that I was able to get with this picture. But this is pretty accurate representation just against the blue sky instead of a nice reddish, almost black sky. So
now, were these captured from at your house, Derek?
This is the local high school. I have to drive up and borrow one of their parking lots to get the right horizon. So
excellent. Now Mercury and Venus on this date. Is this when they were at their maximum height? Well, like their max, like in conjunction. This was pretty close to maximum conjunction. You can see they're quite a bit closer together here. They might have been closer together the 22nd. I think it was cloudy that day. But you can see on the 24th how far apart they've gotten just over 3 days. Right.
So
I did get one of the days when I was out during the day shooting Venus, I did capture some Mercury data as well. And you could see the gibbous phase, but it's so small comparably.
Oh, it's absolutely tiny. I didn't have a telescope with me, so I couldn't really take a view of the shape of Mercury. But even in binoculars, Venus is an obvious crescent. Unfortunately, on the camera, it gets blown out, so it just looks like a white blob. But I tried to take some video and do what Scott was doing, would process the video and see if I could generate this image, but with the phase evident on Venus, and it didn't work out so well. So here we are.
Well, I think it looks great anyway. It's awesome.
Yeah, I was pretty happy with this one.
And now so the moon is now back into tonight's first quarter.
Yep.
And so after tonight, we're going to start seeing the gibbous moon. But if you get some clear nights, I mean, anywhere from like 50%, so like first quarter, all the way up to about 89% waxing gibbous. It's like the best time to look at the moon because all the best craters and features on the moon are all along that sunset line, which is where you want to look at them. So if you get a clear night over the next week, or get out and take a look at the moon. I mean, Friday the 5th is a full moon. Of course, we would end up trying to open our first night on the full moon, but that's the night you don't want to look at the moon.
We have Ken asking you to talk a little bit about the path across the sky the sun and the moon take and how it changes over the year.
Sure. So we're talking about the ecliptic. So the ecliptic is the path the sun takes across the sky, and it's generally the plane of the solar system. So real fast on that, if you were to step off of Earth and jump up above the solar system and look down, you would see the sun in the middle and kind of planets all over the place. But if you could jump to the side and take a look at the solar system, you'd see the sun in the middle, and you would largely see just a line of planets. And that's because all the primary planets generally sit along that plane of the solar system, and we call it the ecliptic. Now, from us in the northern hemisphere, at this perspective, you get the ecliptic will rise and set throughout the year. So in the summer, on the summer solstice, when we're at our maximum tilt towards the sun, 23.4 degrees, that's when the ecliptic gets really high in the sky. So if you think about it, if from our location, if you're to look out at the celestial equator, it's like the projection of Earth's equator into the sky. You would always see it's always in the same spot. But during summer solstice, the ecliptic is about 23.4 degrees above the celestial equator. And that's during the daytime, so you get the sun really high in the sky. But consequently, the ecliptic is going to be about 23.4 degrees below the equator, the celestial equator, at nighttime. And that's when you get the moon at night, it travels along that part of the ecliptic, which is really low in the sky. And that's why you sometimes get the June moon is sometimes called a honeymoon. And that's because if you factor in the moon is just about 5 degrees off of the ecliptic, sometimes above, sometimes below. If you get the moon 5 degrees below the ecliptic in June, it's going to be low enough in the sky this far north where it just stays yellow all the time. And it looks like meat or honey. So they call it the honeymoon. Now, another way to think about it too is wherever you're seeing the moon, for the most part, minus that potential 5 degree incline, at night during the summer is where the sun is going to be during the daytime in the winter. And during nighttime in the winter, when you see the moon out, that's largely where the sun's going to be during the daytime in the summer. Now, being that the moon is 5.1 degrees inclined to the ecliptic means that the moon could either be above the ecliptic or below the ecliptic. And this is why we don't get a total solar eclipse every single month when the moon goes to its new phase, because it's usually either above the sun or below the sun. And about 2 to 4 times a year, you'll get it kind of crosses right over a part of the sun. And somewhere on Earth, we'll get an eclipse. The planets follow the ecliptic too. So if you see, you're not going to see a planet in the north, the same way you're not going to see the sun in the northern sky or the moon in the northern sky if you're in the northern hemisphere. So if you're looking north and you see a really bright star, it's not a planet.
Yeah, so Ken had said that they kind of lost you there, I guess, for a couple of minutes or so. But he was saying the moon sets at different points.
It does. So it depends on what you're looking at is where. So sometimes you look at the moon and the moon will rise, south, to the southeast. Other times it rises due east. Other times it rises a little bit to the east-northeast. It depends on where the moon is in relation to its 5 degrees from the ecliptic. So it can be 5 degrees below the ecliptic, 5 degrees above the ecliptic. The ecliptic doesn't go straight up overhead here. It does that on the equator during the equinox, and the tropics of Capricorn and Cancer will get it on the solstices, depending on which solstice. So from our point of view, it's always on an angle. It's slanted. So if the moon is below the ecliptic, then it's going to rise more in the southeast. But if it's above the ecliptic and the ecliptic is due east, then you're going to see the moon in the east-northeast.
We had another question from Tim Myers. He asked, why do many comets put on a better show in the Southern Hemisphere? Is it due to how our solar system is orientated and the path through the Milky Way?
You want to take that, Derek?
I'll start it. So a lot of it has to do with the direction that the comets are coming from in our solar system. As of late, it seems like a lot of the comets are orbiting from the south of the ecliptic, so they're coming up towards the sun. If you say up is the northern hemisphere of Earth and south is the southern, or down is the southern hemisphere of Earth. So the comets are coming from way out in our solar system, and they're coming in towards the sun, and then they cross the ecliptic, and then that's when we can, or that when they get near the ecliptic, that's when we can start to see them, and then they go around the sun and back down towards the south once they've orbited around the sun, and then they go back out for thousands of years into the Oort cloud or beyond to do what comets do best, which is be frozen. It's only when they get close to the sun and all of that solar radiation, heat, and light really gets them to be active by heating up the surface and energizing the particles that are on the surface of the comets. Not a lot of comets orbit in the plane of the ecliptic, and I think a couple of years ago we probably had a lot of good northern hemisphere comets that were just on the edge of naked eye visible, and it's just right now the collection of comets seems to be coming all out of the south. I think Scott earlier in the presentation mentioned there is one coming from the north. It's coming out of Canis Major.
Yeah, it's Comet U6 Lemon.
Yeah. So, that one is going to be interesting for us because it's like on the day side of the planet right now. So.
Yeah, so Canis Major is kind of setting with the sun right now.
Yep. The sun is basically, if you're familiar with the sky, like right in the Pleiades area of the sky right now. And then, so we've got it. Like very early in the morning, you might be able to see this before the sun comes up.
I mean, you got to think about it too. I mean, everything is tilted and spinning. So you figure, Earth is tilted 23.4 degrees, and we're spinning on our axis. We're also spinning around the sun. And the solar system is tilted quite significantly to the plane of the galaxy. We're tilted roughly about, I think it's almost 60 degrees to the plane of the galaxy. And when you kind of factor all this in, the northern hemisphere just gets the shaft on our orientation. The southern hemisphere gets the center of the Milky Way straight overhead in the sky. You can see the whole galaxy unfold in front of you. You get a really great view of the as these comets. So some of the comets don't necessarily follow the plane of the solar system either. A lot of times they are perpendicular to the plane. Sometimes they're tilted to the plane, and a lot of times they end up coming up from underneath and swinging around and going back down. So in that case, southern hemisphere rocks it. I mean, I don't know if anyone remembers, but what was it, 2011? We had a Lovejoy comet that was so remarkably bright that you were able to, that there were pictures coming off the space station of it. North didn't see any of it. The way it is. So Derek, you want to show some of your deep skies, or you want me to move on to something else?
Yeah, we can do some deep skies. I've got a pile of, a couple weeks ago we had some very nice weather. I was able to go out and basically do a survey imaging session where I took a bunch of quick collections while I was testing out some new gear. So let me open those up and then we'll go through them.
I mean, it's been a really great, last week was just amazing. We were out, like the Milky Way night. that we did. We did our online live stream to celebrate the Milky Way on Saturday night. Every time we're done with our live sessions, we have a post session where we sit around and we talk about the night. We also talk about what to expect the coming week, and sometimes just joke around. And after the Milky Way session, I'm like, I gotta go. I'm running out because it's such an awesome night. I want to go out and do some data collection.
So we'll start at the high end of the Messier catalog. This is one of the largest galaxies from like an angular diameter standpoint, meaning the field of view that it fills when you look at it with a telescope. This is M101. This is in the constellation of the Big Dipper. Right off the end of the handle, there's two galaxies. We'll go to the next one after this one. One is above the handle, one is below the handle. And so this one is it's basically the epitome and definition of what you would call a spiral galaxy. Unfortunately, I lost this one in the trees after about 6 images, so I don't get a lot of detail here. But you can see there's some faint arms that go off this way. There's some faint arms going off to the top of the image, and then they actually go up, beyond what I have actually captured here on this image. But you can see there's the dust lanes, these collections here of denser star clusters. It should be noted these pictures are all monochrome. I don't have any color data yet on these. And then the other one that's in the Big Dipper is this one. This is M51. It also has a companion galaxy that it is interacting with. This one I got quite a bit more data on. This is also a spiral galaxy, and then this is something of a galaxy that's kind of being torn apart by the larger M51 galaxy. And then ever so faintly, you might be able to make it out on the stream. There's like this halo of gas around this galaxy, and that actually tails off in this direction. So I'm hoping to get more data to be able to show that.
This is galactic bullying right here.
Yeah, this is galaxy eat galaxy. And while not the same size, this is kind of the interaction that the Milky Way and Andromeda are going to go through in a couple billion years. Though the Andromeda galaxy and the Milky Way galaxy are actually moving towards each other. The Andromeda galaxy is a little bit larger than we are. I can show that later. All right, so the next one I've got is M100. This is a galaxy that's in the Virgo cluster of galaxies that's behind the constellation. Leo is a much more prominent constellation than Virgo. So this sits to the east of Leo, right behind the back of the lion, or the tail of the lion. There's tons of galaxies in that area. There's two satellite galaxies, or two not satellite galaxies, but two other galaxies in the field of view here. There's another one over here, much smaller and more distant. There's just a lot of galaxies in that area.
Derek, this is an amazing image. How many subframes is this?
20.
And how long is your exposure?
2 minutes.
3 minutes?
2.
2. Is this unguided?
This is guided.
Very nice.
I have not gotten my polar alignment sufficiently nailed in to go unguided for that long.
Oh, okay.
But that was part of what I was trying to hammer out that night, but didn't get there. So going back to Leo, I think that this one's still in the Virgo cluster. This is M98. This one's kind of more edge on. You can kind of see the difference here. This is face on. So we're looking basically perpendicular to the galaxy, down at the whole disk of the galaxy. And in here, we're looking across the disk, and you can see the dust lanes, you can see the core, and you can kind of see the bulge of the galaxy. And again, there's, background galaxies, in a couple of spots in this image. The next one, we're going back to, this is over underneath the front of Leo, under his chest. This is M95. And this galaxy has gone through some sort of interaction in the past, and there's a couple other galaxies in this group that are suspected to be the ones that kind of went through with this. As you can see, it's kind of got an odd shape. It's got this ring of stars with a bar and then a very dense core. Kind of looks like the ripple on a pool after you've dropped a ball in the surface of the pool until that settles out.
But these galaxies are out there too. I mean, Messier 95. This is what, like 32 million light years distant.
Yeah, this one's pretty far. I don't have
this might be a good time to ask this question. Marie had a question. I'm not too sure exactly what she meant by it, but maybe you guys do. She said, "Could you explain all the tilts?" So
all the what?
The tilts.
The tilts.
Mm-hmm.
So, I mean, if we're going back all the way to Scott's discussion about Earth being 23.4, 23.5 degrees tilted, the solar system being about 60 degrees tilted to the galaxy, and the moon being 5 degrees tilted to the ecliptic. Those tilts are all just properties of the objects. So if we start with Earth, because that's where we are, if you picture kind of a basketball or a globe, I mean, a globe is tilted in its stand to represent the tilt that Earth has within the solar system. So if you think of the sun as having the plane of the solar system, Earth is not perpendicularly oriented to that plane. We are tilted, and that's what gives us seasons. As we orbit around the sun, different surfaces of the Earth are more tilted towards the sun or tilted away from the sun. And we in the Northern Hemisphere, when we're tilted towards the sun, we call that summer. And the Southern Hemisphere, summer is actually in December, because that's when the Southern Hemisphere is tilted towards the sun, 6 months apart. And then for the moon, whatever formed the moon, it has stabilized into an orbit around Earth that is 5 degrees off of the ecliptic. I'm trying to think if that's right. Or 5 degrees off of, basically the line, the projection of Earth's equator into the solar system. And that's, as Scott was saying, when the moon passes between Earth and the sun, sometimes it crosses the direct line of sight, and that's what gives us a solar eclipse. And in the opposite case, when the moon gets behind Earth, so Earth is in the position between the sun and the moon, we get a lunar eclipse. That's when Earth's shadow is projected onto the moon. A solar eclipse is when the Earth's shadow is projected. Sorry, a solar eclipse is when the moon's shadow is projected onto Earth.
Derek's been social distancing a little too long.
Yeah, maybe. So, and then then if you take the whole average of the solar system and then compare that to the average of the galaxy, the Milky Way, the solar system is tilted 60 degrees. And probably rotated such that the southern hemisphere of Earth is, has a better view of the galactic core and some other fun objects that we in the north would love to be able to see, like the large and small Magellanic Clouds.
Yeah, the satellite galaxies, right?
Yeah, the Milky Way has satellite galaxies. A lot of people that live in the northern hemisphere don't know that because they don't ever see them. They're very large, diffuse clouds in the sky that are satellite galaxies and probably remnants of galactic mergers that the Milky Way has gone through in the past. I'm going to stop there and let the feed is a couple, about a half a minute behind, and see if I was going in a direction that helps you or if inspires more questions.
Well, there was a question from a little bit ago by Tim, and we're talking about the Southern Hemisphere. He wanted to know if anyone here has ever spent any time down in the Southern Hemisphere to observe their skies.
The farthest south I've been, Tim, to observe. This definitely isn't the farthest south I've been, but actually to observe was Mauna Kea on the Big Island in Hawaii. And of all the places that I've been to look at the night sky, I'd have to say that I haven't really found one that really blows the doors off of the darkness at Frosty Drew. I get comparable views of the Milky Way or darkness at most of the places I go, but not Mauna Kea. When I was at Mauna Kea, it blew my mind how easily visible the Milky Way was and how much higher it was as well. And the constellations changed a bit. It was quite amazing to see it from there, but I haven't been any further south. So we do have some of our interns that have spent time in numerous countries around the world, either on internships or fellowships or different parts of their academia to get their PhDs and their degrees. And one of our interns, her name is Amelia Henkel. She's a fabulous intern that graduated UConn with a physics degree. She spent all last summer in South Africa working for the International Astronomy Union in Cape Town. And the views that she got of the night sky, they're breathtaking, amazing. How about you, Derek? You been down there?
I have not. I think the furthest south I've been to do any observing is probably North Carolina. Not very far south.
Derek gets out there, huh?
Well, yeah. So not for astronomy. I mean, I've been further south, kind of, but I've never done purposeful astronomy. So there's that.
As far as it goes for me, I'm not a hot weather person. If I go down anywhere along the equator, it's murder for me. I'm just sitting there in my boxers, sweating all over the place, and people look at me like I'm like something wrong with me, and it probably is. But so I tend to go north during the winter when I want to go somewhere. So I'm more looking for the northern lights and stuff like that. But
I think Tim, one of our viewers here, Tim, was right along there with Derek. He said he's been to the Outer Banks of North Carolina in October.
Yes.
Really dark skies there.
Hatteras Lighthouse is probably where I will say I've seen the darkest Milky Way I've ever seen. When they had the whole thing decommissioned while they were moving it, I was out there. It was crazy. So, all right. I guess we'll continue with my galaxy tour. I'm going kind of quick, but
well, another thing, real quick about and this plays in with the galaxies you're showing us, Derek, is that tilts apply beyond the Milky Way galaxy. I mean, so Derek's got M95 up right now, and a little bit before that, he had Messier 51, the spiral galaxy that's bullying the smaller galaxy. That one right there. There are orientations and tilts everywhere in space. And the real question comes down to what's up and down? What's the top and what's the bottom? There really isn't an up and down in space. We have it on Earth because we consider up and down, the sky above us and the ground below us. But what if you're in the Southern Hemisphere? Everything in the sky in the Southern Hemisphere to us looks like it's upside down.
Yeah.
But if you ask people in this...
One thing to note right there is we sit at a latitude of 42 degrees. If you go 42 degrees south and then you put those two people together, one would be laying down, one would be standing up, because they would be almost 90 degrees to each other, but they have the entire surface of the Earth in between them, so they both think they're standing upright.
Right. We had a potential intern visit us from New Zealand, and we were looking at the sky, and I was like, oh, and she's like, I'm like, the moon's upside down for you guys down in the south. She's like, no, it's upside down for you guys up here in the north. So, but when you're looking at these galaxies, sometimes you see galaxies like M51 right here, where you're actually looking right at the galactic plane from what would look like either the top down or the bottom up, where you see the spirals, you see the galactic nucleus, and you get a fabulous view of it. But that's not the case with everything. Sometimes we see galaxies on edge, where it's just a thin line and a bulge in the center. Sometimes we see galaxies on a tilted plane, like the Andromeda galaxy. And there really isn't a proper orientation in space. Your orientation, as far as humans perceive up and down, comes down to gravity.
Well, Ken had another question here. With the photography that he's seeing here, can we see these views at Frosty Drew or just through photography?
That's a really good question. This view with this much detail, you would not see with a telescope that we have at Frosty Drew. What you would see is you would definitely be able to see that there's two components here, and you might be able to see some of the dust lanes eking through, and just ever so faintly being present. But these objects are extremely faint. This image here represents 40 minutes of collecting light through a telescope and then processing it to further bring out detail. And the human eye, you'd need a rather large instrument to be able to start to see this level of detail without photographic data.
And that's exactly it, Tim. It's that there's a lot of factors involved in it too. So when you're taking images here like Derek is, and he's capturing all this detail, he's got a lot of room to play with. So he can process out some of the light pollution. He can process out some of the haze. He can isolate wavelengths of light or specific types of light that he wants to capture to give him a better view. When you're looking at this through a telescope, everything is in real time. You got to deal with the localized conditions, the light pollution. You got to deal with haze. You got to deal with atmospheric issues. You got to make sure if your telescope doesn't have enough aperture, do you have the right eyepiece in? And it also comes down to how seasoned or how experienced of an observer you are. When I look at this object in a telescope, instantly I see the 16-inch down at Frosty Drew. I'll see the spiral arms. I see the little dust lane in the bridge between the two galaxies. I mean, I can see everything that's going on. I can see some of the brighter bands in the spiral arms because I know what this galaxy looks like. I know where to look for them. But if you don't look through telescopes a lot, and if this is your first time looking through a telescope, and I say, hey, take a look, this is a galaxy, you probably wouldn't even notice it. Because like Derek said, it's very subtle.
When I'm describing to people what to look for when they look through a telescope at Frosty Drew, I generally describe things as like a fuzzy, pulled apart cotton ball on a black sheet of paper. And that analogy has worked really well for a lot of people because they have said, I would have just glanced over that, little fuzz and said, that's nothing. I don't see the object. And in fact, you are seeing the object. It's just the level of light that we're getting to the eye is still so little compared to what you can do with a camera that it registers against the background blackness of space, but only just.
So this galaxy here, I mean, this is 23 million light years distant. You're looking at the combined starlight of all the stars and everything else in that galaxy. So like Derek was saying earlier, galaxies are dim. I mean, and it's hard to isolate specific wavelengths to get a good view of them because you're looking at pretty much everything. You're looking at broadband starlight. So they are quite dim. And we've noticed at Frosty Drew that sometimes you get a night where you think, oh, yeah, it's going to be an excellent night to look at galaxies. You take a look in a telescope and you don't see anything. And you get other nights where it's like, oh, it's kind of hazy tonight. You take a look and the galaxies are just popping out.
Yeah, it's very strange. Some nights you would think these sky conditions are terrible. And for whatever reason, that's the right combination of moisture in Earth's atmosphere that it enhances the view.
Yeah.
And other nights, there's too much wind and you get nothing.
Right.
Well, I know Ken is saying here right now that it's hard to see through the telescope. And he says that's why these programs have been so helpful to see more and better and have more time for your explanations.
Awesome, Ken. I'm glad that's a great point of view. I love that.
Absolutely.
Yeah. So the next one I've got here is actually got a cool nickname. It's called the Black Eye Galaxy.
Oh, nice.
So this one's a little bit weird. I still haven't done enough reading to understand why, but it just looks way too smooth. Like this galaxy doesn't have a lot of definition other than this giant blob of a dust lane across the core. And it's just, to me, it looks a little strange. And, you know, to try to describe what this looks like visually, you see kind of a circle of light and then this bar of black across it. You don't see all this, you know, faint detail around the outside of the core there. But we can actually zoom in and you can kind of start to see that, you know, this dust lane here is just really wide compared to most galaxies. And it really obscures a lot of the light that's coming out of the core of that galaxy.
So what's going on here is, and the reason why you get that really dark dust lane like that is this galaxy here is a product of a recent galactic merger. And what's happening is the initial galaxy, which was perturbed, has a secondary galaxy settling into the galactic plane, but it hasn't fully settled in yet, and it's sitting right above the galactic plane. And all of that cold hydrogen gas from that secondary galaxy is all chunked along that dust lane right there. And that's what gives us that really thick dust lane around the galactic nucleus. So if we could, and this is like what Derek was saying before with tilts, if we could change our orientation just a little bit, we would be able to see that distinction. But from the angle that we see this slightly tilted, it looks like they're, you know, together. That's a fabulous image, Derek.
Thank you.
Now you're capturing these with your 1600, right? Your ASI 1600?
Yeah.
Now are these just luminance, or are these a specific wavelength?
Yeah, these are full broadband.
Okay.
I don't even have a sky glow filter in. I'm just wide open. And then the last one I've got is a cool
That's
pairing.
amazing.
Wow, look at that.
This is it back in the constellation of Leo, at the tail end of Leo under the back leg. There's actually 3 galaxies called the Leo triplet. The third one is actually off the frame to the bottom. I couldn't quite fit it, so I just centered these 2. But this is Messier 66 and Messier 65. And you can see this one, you know, has a very traditional shape, looks kind of like a spiraled galaxy. I think it's a barred spiral. And then this one is obviously perturbed and, you know, has kind of a disorganized state going on. And these are quite evident in a telescope, even of a you know, 8-inch. I've seen these in a 6-inch telescope. In an 8-inch on a good night, you can see the third one as well. I don't think I've seen the third galaxy in anything smaller than an 8-inch telescope. And really what that is all about is the size of the mirror or the lens on the front, if it's a refractor, really control how much light is being gathered and presented to the human eye for, you know, processing by our brain. And if you look at the area of an 8-inch circle versus the area of a 6-inch circle, it's almost twice as much light.
How far apart are these 2 galaxies?
I think they're around 30 million light years away. As far as how far apart they are, I don't know.
These galaxies are probably about maybe about a fourth of the distance that the Andromeda galaxy is from us. I mean, they are part of the same galactic grouping. And you're right, they're about 35 million light years distant, both of them. So, but this, and as earlier question we had, and as Derek was saying, this is a fantastic image. You would not see this level of detail in the Frosty Drew telescope when looking at this object. You would notice the irregularity, and you would notice the tilt of M60, 65 and M66, the irregularity, but what you wouldn't see is just all this detail in these dust lanes. This is such a great image. Can you blow it up a little bit, Derek? Yeah, look at that. That is excellent. You can see, so in this image here, I mean, take a look at it. So it's a perturbed galaxy, but you can see the spirals. You got one coming off the left of the bar and then one coming off the right of the bar. And I mean, you can see the dust lanes along these spirals. I mean, this galaxy is very active right here. And note the tilt. So in this case, this galaxy is tilted. It's perpendicular to our point of view, and it's also tilted to the side. Again, this is the ups and downs in space, you know.
Right. And the other thing that I find crazy is this tilted? Is this side tilted away, or is this side tilted away? It's one of those things that you don't have enough information to know.
Marie is asking, can you explain perturbed?
Oh, okay. Perturbed means like if you had kind of a bucket of marbles and you dropped, you know, a larger object into that or something, the marbles would go, you know, in all different directions and then would eventually settle. So some event has happened to this galaxy to disturb its organization, and it's going through a process of settling after that event that perturbed it or disturbed it, to use a different word.
Yeah, so any kind of interaction with another galaxy on a galactic level will perturb, or Derek was saying, disturb the organization in that galaxy. But this happens too with stars as well. When you think about stellar evolution, as stars move through their fuels, they go through perturbations, you know, stalls and that. Anything that disturbs the organization of that star's mass and matter, and we call it perturbations.
I just have to say out there from the chat, like Ken just said, that is a wow.
Yeah, this is a great image.
Really is.
All right, so
thanks, Derek, for all these great images tonight.
I know. I was like out there for like, I don't know, 4 or 5 hours for 3 nights, just hammering away at objects, just collecting data. I got a new toy. It was nice to have a couple nights to actually use it.
Dedication. That's a new toy.
So this is moving out of the Messier list and into the NGC list. And we had a question a couple weeks ago about what does NGC stand for, and it is the New General Catalog. I got it right this time. Whereas the Messier list is named after a person from the 1700s who cataloged items. The NGC list is a more modern list that it contains a lot of the Messier objects, I think all of them, but it has a lot more other dimmer and fainter objects on it. So this one is actually a galactic merger that's starting. So you can see, actually, do I have the, yeah. So this is NGC 4567 and NGC 4568. This is in the Virgo cluster that we've been showing galaxies from, that is behind Leo, and you can kind of see that, you know, these two are starting to merge along this front here, and they haven't really completed that merger, and their overall level of, you know, disturbance is minor, so you can still see the original structure of both of these galaxies. Whereas I learned tonight, M64 is kind of like the Black Eye galaxy, going back to this one, is kind of where the merger event is nearly complete.
Yes.
And then I have, oh, sorry, you can talk, and I'll bring up the next one.
No, this is just excellent, because if you look along that axis, you know, these two galaxies, as they come together, they're definitely on different orientations or different tilts, but right along that line of connection, we're starting to see a nice increase at this point in star formation along that region, because all the molecular hydrogen, all the nebulae in both these galaxies is starting to mix together, and that is the perfect recipe for star formation. So you're already seeing an increase in star formation along the parts of these galaxies that are starting to connect.
So Marie says, fabulous images, Derek. Technically great. You can see your passion.
Thanks. Yeah.
Oh, yeah.
I parked this hobby for a couple of years because I got super frustrated with it. And, you know, so I was glad to pick it up again. So, all right, the next one is, again, galactic mergers. So this one hasn't, this is a very edge-on galaxy, and this here is another galaxy that is moving towards it, or as I've been reading, these two are, further apart than these two, and then even more further apart than these two. But it's kind of interesting to be able to see different galactic or galaxy pairings and see what's going on with them. And you can really start to see, even at the amateur level, like, a lot of the science has been done around these two galaxies, but you can read about it and then say, all right, well, I can collect the data on that and see if I can reproduce some of it. And just to see, just from like a science standpoint, if it's something that's reproducible. So it's kind of interesting. It was actually, when I was processing this image, I think it was this one, or maybe it was this. No, it was this one. I was looking at the galaxy and I was like, hey, that's a really bright star. And I went and looked at like a Hubble reference of this, and this one wasn't super bright. But I think that's an artifact of my processing and not, a recent supernova, which I was really hoping for.
That would have been awesome.
That would have been awesome. Speaking of, I was in this area of the sky. There's a galaxy M61, which I don't have any data of, which actually had a recent supernova, and there was one astrophotographer that was taking images of this galaxy every couple of nights. So he has the before images and the after images, and it's pretty cool to know that, like, even at the amateur level, he has that data, and it was useful to science somewhere.
Right. Everyone can contribute.
Yep. It's pretty crazy. And then this is the last recent galaxy picture I have. This is in a series of galaxies called Markovian chain. Markarian chain. These two are known as the eyes. And they are, interacting galaxies, and you can kind of see the dust lanes of this galaxy are very disturbed, and this is the suspected galaxy to do it. And in this field of view, you've got this big galaxy that is what is known as an elliptical or lenticular galaxy, where it has basically no structure. It's just all stars, and it is basically a giant ellipse in shape. Down here, you've got probably an edge-on spiral galaxy, based on the dust lane there. And then, you got some background galaxies over here. And then the final image I have for you is taken with a different lens. It's a wide angle of Markarian's chain. Just to give you an idea, these two right here are the eyes that we were just looking at. And then this big bright one is that, I think it's M86. So you can really see like this chain of galaxies here, and then just there's a background, there's more galaxies over here, and more galaxies over here. So just in this field of view, there's probably 20 or 30 galaxies. And this field of view is probably, if you put your hands next to each other in the sky, it's that wide, at arm's length.
Yeah, those are excellent images, Derek.
Yes. And then because we talked about it, let's go back and talk about, where are we at? Andromeda. So that's our galactic neighbor, the Andromeda galaxy. It's 2.3, 2.4 million light years away. This is naked eye visible at Frosty Drew, and it is an awesome object to look at it in with binoculars. From this edge over here to this edge over here is about the same width as the 5 or 6 full moons. So this object is very wide, and it has 2 satellite galaxies. This is M110 and then M32 right here, and then all the other background the stars in this image are local stars to the Milky Way.
So a question that And then the
Go.
question that was out there now is that how do astronomers know something is 31 million light years away or whatever the distance? How does that kind of time and distance get computed?
So there's a lot of different methods. Some of the things that are closer we can actually do with parallax measurements. And what that means is we kind of use, excuse me, I'm going to mute. I have to cough. Scott, if you want to start that discussion.
Yeah, so parallax. So when we measure objects that are in the galaxy, or in the closer part of it to the galaxy, the method of parallax is pretty easy. So think of it this way. You could practice this on your own. If you take both your hands, take your fingers and point them towards the roof, and then put your left arm at arm's length in front of your face. And then put your right arm in line with that other finger, but half the distance. And then with keeping your hands still, just move your head from side to side. And you'll notice that the finger closer to your face will cover a much larger area than the finger further away. And you're also crossing over the farther finger. So what you're doing is you're creating triangles here. So using that principle, we can measure stellar distance. And the way we would do it is, let's take the North Star, for example. So say it's the autumnal equinox, the first day of autumn. We take a telescope, we take a look at Polaris, and we chart Polaris, and all the stars behind it. We take a picture of it. Now we can do it. Then we wait 6 months. And this is an old way of doing it. Now we can do it with our satellites in much quicker time. But you wait 6 months, you're on the other side of the sun. Now you take an image again of the same field, and you measure how much Polaris appeared to have moved among the background stars. That motion, that movement is just due to us jumping 2 astronomical units, the distance to the sun and then that distance again. And you take that shift, make a triangle out of it, cut it in half, and then measure the angle of that triangle. Take that angle and then hit the tangent of the angle and times it by the distance of the Earth from the sun, 1 astronomical unit. And then we can get the distance to Polaris in astronomical units. So that's how we measure objects that are closer to us. But that's not going to work with galaxies. The distance is just too great that there's nothing we're going to have in our local neighborhood that's going to give us enough motion to get a parallax measurement. So when we measure galaxies that are far away, we use something called standard candles. And this is where supernovae are really important. So a standard candle is an event that happens in space that is always the same brightness and the same activity. So it always looks the same. One example, this would be a type 1a supernova. A type 1a supernova, I'm not going to go into great detail about it, but when a type 1a supernova happens, that reaction that happens, that explosion, always occurs at 1.44 solar masses, which is called the Chandrasekhar limit. When that happens, all of that mass, all of that matter ignites and you experience thermonuclear runaway. So since it's always at 1.44 solar masses, it's always exactly the same brightness. Now, we can tell it's a type 1a supernova by what Derek was describing earlier about the astrophotographer who has all the data of a supernova that's occurring right now from before it happened and all the way through its brightness. If you graph that brightness trend, you get something called a light curve. And that light curve will give you a signature of the type of supernova that it is. If it's a type 1a supernova, since we know exactly how bright it is, it's like being able to measure the distance of a car based on how dim the headlights are from our point of view, because we know how bright the headlights are. We could use that event to measure the distance to that galaxy. We can also use an object called a Cepheid variable. Cepheid variables have a period of, so it's a variable star, so it has a bright period and a minimum period. And this period is largely the same amount of time, and they all the same max brightness and the same dimness. Now, when we identify a Cepheid variable, we can identify it by its period of variability. And once we identify a Cepheid variable, we wait till it's at its brightest, and then we can use it to measure a distance to that galaxy. And that's only going to apply to galaxies that are relatively close to us, because when you get way out there, you're talking, a billion light years, you're not going to see a Cepheid variable in that galaxy. So these are some of the methods that we can use to measure distances. There's more, but these are some of the more common methods.
Can I ask another question?
Yeah, shoot.
Since I have all these wonderful pictures of these galaxies, Ken is asking, what creates the spiral effect of the galaxies?
So my understanding of what creates that spiral effect is actually tidal drag. And what that really is, we're going to look at the Earth and Moon and talk about that for a little bit. If you look at when high tide is and when the moon is directly overhead, the tide is behind the directly overhead time for the moon, because the water lags behind the moon because it has mass. And a similar thing happens with the galaxies. The core of the galaxy is rotating. That imparts an angular momentum or an angular velocity onto the mass in the galaxy. And as that, propagates through the galaxy, there's a drag associated with that propagation that ends up causing the matter to pile up into the spiral arms that we see. I'm not, a professional astronomer. I do this as a hobby. So that's kind of my understanding of how it works, based on my reading through books and some other, articles on the web. I'm actually curious to see what Scott says.
Well, so you're right. So the tidal drag, I mean, the mechanism here is gravity. So it's the gravitational forces of the more massive objects, in this case, that central black hole. And as it's pulling everything along with it, these objects get close enough to each other too, where you get an overall, clumping of massive objects through gravity. The organization of the galaxy is a result of all this spinning. You have star formation along these regions, and these stars do stay clustered together for a period of time. The molecular clouds will stay clumped together as well due to gravity of the surrounding area. And you also have a lot of dark matter that plays into this as well. Dark matter will it's almost like, you could think of it, though it's not, you could think of it like anti-gravity in a way, where though it interacts with ordinary with gravity, it doesn't necessarily interact with ordinary matter. So it has an effect where it kind of pushes everything together. A good way to think about dark matter is think about like a wave in the ocean. And as the wave is moving in and out, it's picking up things on the surface of the water and clumping it together in the waves. And then all that movement kind of keeps it clumped together. That's kind of how dark matter works with galaxies. And once the galaxy's got all this matter clumped together, that tidal drag that Derek was describing, that supermassive black hole is spinning. It has a residual pull on all that matter and mass in the galaxy due to its gravity. And it starts to drag everything along into a spiral formation. So that spiral formation will come apart when there's a galactic merger. But even though a galactic merger occurs, as long as you have cold hydrogen gas or nebula in that galaxy, then you're going to get star formation, and you're going to eventually form into another spiral galaxy until you use up all that hydrogen gas, at which point star formation stops, and you end up at that point more like an elliptical galaxy, which is just an ellipse of old stars.
That's the boring galaxy.
Yeah.
They're not fun to take pictures of. So I have one more galaxy from my historical data. This is M33, which is the Triangulum galaxy, and it's in the same area of the sky with Andromeda. If you look at the tail coming off of the square of Pegasus, Andromeda is above the tail, Triangulum is below the tail, and it's a much smaller galaxy. This was taken with the same telescope that's taking, like this picture of M101. So M101 and Triangulum were taken with the same telescope, different cameras. They basically have the same field of view, and you can kind of see that, you know, Triangulum is kind of an interesting galaxy, at least from what I can see, in that it doesn't have a really strong structure. It's kind of a loosely structured galaxy, and you know, that has its own interesting characteristics, and it's a much smaller galaxy as well.
Yeah, I mean, so, and as Derek is saying, you know, this galaxy takes up more of the field than M101 did in that recent image, but M101 is not part of the local group, which is the group of galaxies that the Milky Way is part of. The Triangulum is. So Triangulum isn't tens of millions of light years distant. This is only about 3 million light years distant from us. And like Andromeda Galaxy, this galaxy will eventually merge with Andromeda just like we will. Now, Triangulum is one of the 3 primary galaxies in the local group. I mean, you have from largest to smallest, you have Andromeda, the Milky Way, and then Triangulum. And if we look at Triangulum in a telescope at Frosty Drew, though this is a rather bright object, if you think about it, because it takes up a pretty good area of room in the sky, there really isn't any specific bright area. So looking at this in the Frosty Drew telescope is difficult because it's really big, so it fills up the field of view. And there's no one spot that really stands out that bright. I'd say the most visible spot of it is probably kind of right along the spiral that you see kind of to the bottom right. That kind of stands out. And the galactic nucleus looks like just a slight glow.
Yeah, it definitely doesn't have a strong defined center point like Andromeda does. Like when you look at this through binoculars, like this galactic core is obvious, and then you can start to tease out some of this, you know, dust lane, and you know, way over here there's a really bright cluster in Andromeda that you can sometimes get in a telescope.
So Ken had a follow-up question, and he said, what causes the spinning?
So everything is spinning in pretty much in space, Ken. And what's causing is on the galactic scale, it comes down to, again, it comes down to dark matter, it comes down to that supermassive black hole in the center. But as far as what generates a spin on the galactic level, I really couldn't answer that. What generates spin on the stellar level, it comes down to the formation of the star. And that star starts to spin when it's collecting all of that mass around it. And once that reaction starts, now you actually have a functional angular momentum or spin. And the same thing goes with planetary formation. You know, as all that material or mass in this scenario, it gets collected, it collects in a spin and it starts spinning the object. Now the Earth spins a lot faster than you would expect. And that's largely due to a product of the formation of the moon, where Earth was impacted by a very large object that was also forming in this orbit, another dwarf planet, which set Earth spinning very quickly on its axis. And then as the moon formed, it took away some of that spin. And you think about it, you know, energy isn't created or destroyed, it's just borrowed. So as the moon formed around the Earth, the moon started to pick up some of that angular momentum from the Earth, and it slowed the Earth down a little bit. But once the ratio of the spin of the moon matched its orbital velocity, or its speed of its orbit, which is called tidally locked, then it doesn't collect any more angular momentum. Another way to think about it too is every time we use a satellite or a spacecraft to slingshot Earth's gravity to go faster, we slow Earth's spinning down just a little bit. So do you have anything else, Derek?
I mean, that's from a galaxy standpoint, I think that's pretty much it.
I mean, this is really great too, because so this is the last event we're doing in May, and May is Galaxy Month. And the reason why May is Galaxy Month, because all of these galaxies that Derek is showing us tonight, these are easily visible this time of the year. They're right after sunset, right after, you know, twilight ends, they're pretty much right up at the top of the sky. So this is the best time of the year to be looking at galaxies.
I mean, this is another triplet in Leo. It's about halfway down the body of Leo, underneath between the front leg and the back leg. And if you think of Regulus as the front leg and then the star behind Regulus as the back leg. And these are, you've got basically two elliptical galaxies, and then this very faint one here. I need to collect more time on the telescope to get enough light, enough data to process these out. Probably longer images as well to get this one, because you can barely see it even in these photos. But you know, this is a nice galactic trio. I think these two are quite evident in a telescope. This one probably not so much.
Can you jump back to the Markarian's chain image real quick?
Sure. Maybe. Yeah, there we go.
So let's see here. So you have the chain right here. So this guy right over, so up to the, I think it's the top left.
Top left, this one?
Yeah, that guy there. Is that looks like it's 78, right? That looks like Messier's, I'm sorry, 87.
Yeah, that's 87, yeah.
So Messier 87, guys. I mean, let's look at this for a minute. Messier 87 is a humongous elliptical galaxy. And Messier 87 is the galaxy that we all saw that amazing picture of the black hole that was captured by the Event Horizon Telescope. And that black hole is big. Like we're talking, it's bigger than the inner solar system. And that picture of it, that's the galaxy it came from. I mean, that galaxy is intensely large. And I always try to point that out because that very well could be the most massive object in the Virgo cluster. And I mean, this galaxy is pretty far too. I mean, you're talking that roughly 16, or I'm sorry, it's about 53 million light years distant, this galaxy. I mean, this is out there. And to be able to get an image of that black hole like that, you know, something that's about the size of the solar system, that really is. That's just amazing.
That was I remember reading the articles about that. That was a pretty fascinating thing to read about. And I'm also a computer engineer, so it was fascinating to me to understand how they were collecting the data, storing the stuff on, you know, it was you know, beyond what, you know, like it was just amazing how many different hard drives they needed to store all the data that they were using to process that black hole image. It was, you know, they basically invented technologies to manage the data so they could do the science that allowed us to understand the structure of that black hole. It's fascinating.
And what Derek's describing, in doing so, they effectively made a radio telescope that had the aperture of Earth's diameter. That's awesome. But I mean, look at that galaxy real quick. I mean, just consider this. The Milky Way galaxy is 100,000 light years in diameter. And that's a lot. That means it takes 100,000 years for light at the speed of light to cross the galaxy. M87 here, that galaxy, 980,000 light years in diameter. That's almost 10 times the diameter of the Milky Way galaxy. That's how big that galaxy is. Thanks, Derek. I just wanted to see that again. I wanted to make sure he pointed that out.
That's crazy.
I mean, I have that black hole picture here. If you want me to throw it up.
Yeah, let's go for it.
Yeah, so real quick here. But now, here we go. So this is the picture of that crazy black hole that we saw. And hold on, that's not it. Give me 1 second.
That's not a black hole. That's a pancake.
That's a bunny with a pancake on its head. All right, there we go. That's a black hole. The other one was not. So yeah, so this image here, I mean, this is a picture of a black hole. As impossible as that may sound, this is it. Now, but something to keep in mind here. This right here is not the event horizon. Now, the event horizon is a point at which light cannot escape the black hole. So that's what makes it look like a hole, is if you're looking at the event horizon, in front of you, you have no light at all. It's as dark can be, and it's round, and it's kind of warped around it. So it looks like you're looking into a hole with nothing there, just darkness. This is the shadow of the event horizon. I mean, you can't capture an image of the event horizon. There's nothing to capture. This is the shadow of the event horizon. And what you have around it here, this is an accretion disk. And what you see here is accretion disks are a bunch of mass and matter that ends up dropping into the black hole's gravity, and that ends up spinning around the black hole. And then as this matter approaches the event horizon, it starts to become superheated, super hot, and it releases a whole bunch of light in all different parts of the spectrum, mostly in X-ray. But depending on how big this accretion disk is, those X-rays will heat up other parts of matter inside this accretion disk and allow them to sometimes even emit light in the visible spectrum. So what you're looking at here is the shadow of the event horizon among that massive accretion disk around this black hole. But inside here, the event horizon is a little bit smaller than the shadow, and that event horizon is bigger than the inner solar system. I mean, think about that. That's a crazy big black hole, and that's an awesome image. So, do you have anything else, Derek, or you want me to show some pics real quick?
I think I've gone through everything I've got. So if the questions have settled, I say let's do some other stuff.
So yeah, let's hand it to Derek for such an awesome amount of information tonight. Way to go. I mean,
that was really awesome, Derek.
The Galaxy Gauntlet.
Now, the Galaxy Gauntlet.
Love
Now,
it.
think about it this way. Derek is out there in his observatory, though he's got to work all day long, and he's got a newborn baby, and he's got another young baby. Derek is out there capturing these photos for you, so you guys can enjoy a little wee bit of the cosmos in the comfort of your homes. So that's dedication. So, yeah. And Derek is a fabulous example of the kind of team members we have at Frosty Drew.
Thanks, Derek.
Yeah, thank you, Derek. That really was quite amazing. I was almost like, I'm just going to sit back and let Derek do it tonight. Yeah. I was going to pet the cat, you know?
That's my thing, though. I like to take these pictures and then go read about them and then try to absorb the information and, you know, be able to tell a better story for the visitors at Frosty Drew. So.
And Derek has been on the team for about a decade now. So he's been there pretty much as long as I have. So
crazy. And
it's we every time Derek comes out, we're like, yes, Derek's here. It's going to be an easy night. So now, I've been doing some work on some of the images that I've been capturing over the last couple of weeks, and this is a version of the Milky Way shot that I captured during a Lyrid meteor shower. But in this case, I've been able to process out more information from the Rho-Ophiuchi cloud complex in this image. Now, I wanted to kind of use this as a starting point to showcase a few different things. So we'll start real fast with this section of the image. So this is the Milky Way galaxy. So we've been looking at galaxies all night, but this is what the galaxy we live in looks like from our vantage point on Earth. Now, you have a lot of dust lanes, you have a lot of hydrogen, you have a lot of spiral arms. But right over here, you got this bright star. This is called Antares. And Antares is a supermassive red giant star. And it's bright enough where it illuminates a lot of that hydrogen gas around it. But there's a lot of other activity happening here. Now, if we zoom in a little bit on this part of the sky here, you get the Rho-Ophiuchi cloud complex. And this star right here is Rho Ophiuchi. And this entire cloud complex is rather close to us. This is about 460 light years distant from us. And you have some star formation here. You have some reflection nebula here. You have some binary stars here. This is definitely an area of very much activity. And it is one of the closer sites of star formation to the solar system. Now, the star here, this is Antares, and this is a reflection nebula around Antares. So what a reflection nebula is where the bright starlight from a star that happens to be in a nebula, whether it's the nebula it formed from or a nebula that's passing through that region of space, that will illuminate all that hydrogen gas. Typically it's blue, like you see right here with the Rho Ophiuchi star, or up in this region over here. But since Antares is a red giant, you get all of that yellowish red illuminating that nebula. And we call this the Antares Nebula. Now, this star up over here to the right, this is called Alniot. And this star here has a nice little bit of a nebula around it too. And you can see a little reds in, some of these reds in here. This is an emissions nebula. And what you're seeing here is a lot of that hydrogen gas is being excited by all of the ultraviolet light that's coming off of this star. And it's causing these atoms in these hydrogen atoms to ionize. And when they recombine with their electrons, they get excited and then they emit a little bit of energy in the form of a photon when they come back to a restful state. And you have all of these wisps over here. These are all dark nebulae. And then you're just looking at is parts of the hydrogen gas cloud that are closer to us than the starlight or ultraviolet radiation that's interacting with them. So the side we see is just rather dormant. Now we're going to zoom in on just this section right here. Get a better look at that. So right here, we have Antares down here. And right over here, we have the Messier 4 globular star cluster. So this is a cluster of hundreds of thousands of stars that are all gravitationally bound to each other. And though it appears to be close to Antares and the Rho Ophiuchi cloud complex, it's not. It just happens to be on the same line of sight. So we're looking through the cloud complex at that object. And Messier 4, like most globular clusters, is tens of thousands of light years distant from us. Now, right over here, you have this fantastic hydrogen cloud that is being ionized by all the ultraviolet light coming off of the star. Over here, we have a little reflection nebula around this star that's just a little bit closer to us than the larger part of this gas cloud here, which is being illuminated by Antares. But this blue star illuminates it with blue light, and that gives us a typical view of a reflection nebula. Now, Rho Ophiuchi is up here off of our screen, but you do get this little bit of a reflection nebula in here and all of this dark, wispy hydrogen gas. Over here, you have what looks like a lot of brighter gas in the background. And this brightness you see here is what we call the Integrated Flux Nebula, or IFN. And the Integrated Flux Nebula it's gas. You're talking again, it's hydrogen gas. I mean, it's just hydrogen is everywhere. But this hydrogen gas is not being illuminated by any one star. It's not being ionized by any one star. It's the overall stellar collection of the galaxy, casting that combined starlight just onto that cold hydrogen gas and just slightly illuminating it. This is something that was recently discovered because you need very sensitive cameras to be able to capture the Integrated Flux Nebula. But with modern technology, you can now buy these in the prosumer marketplace. So let's jump back real quick to the picture of the Milky Way here. So that was this region here, the Rho-Phaiki cloud complex. And we largely zoomed all the way into this area right here. But another part of the galaxy, the galactic nucleus right here. This is another fabulous area of interest. Now, you have this dark area that kind of cuts across the center here. And what you're looking at there is the Scutum Centaurus arm. It's one of the spiral arms of the Milky Way galaxy that resides in between us and the galactic nucleus. And it blocks our view of that galactic nucleus. And though the galactic nucleus is right about here, there's a lot of really awesome features along this spiral arm, nebulae and star-forming stellar nurseries. So we're going to zoom in on this area right here. So this here is the galactic nucleus, and largely the constellation Sagittarius right here. Now, if you look along the galactic nucleus here, you can see a very clear view of the Scutum Centaurus arm. And on that Scutum Centaurus arm, you have some nebulae over here. This is Messier 8, the Lagoon Nebula, and this is Messier 20, the Trifid Nebula. And both of these are areas of star formation. Though they don't sit along the galactic nucleus, they sit along the Scutum Centaurus arm. And all of this wispiness you see around here, this is just cold hydrogen gas, we call it dust lanes, that are all sitting along the Scutum Centaurus arm that we see obscuring our view of the galactic nucleus. So let's take a look at this region right here. We'll call it the Messier 8 field. So the Messier 8 field is right here. And in this image, we have the Messier 8 star-forming nebula and the Messier 20 Trifid star-forming nebula. This is also called the Lagoon. Now, inside the Lagoon Nebula, you have active star formation that's occurring. Now, this is about 5,000 light years distant from us. There's a substantial amount of nebula, different nebula types you see here. So inside here, you got a slight bit of blue. You also have a bit of blue right here. These are reflection nebulas. And what you're seeing here is just the starlight from all of that, those young, hot, high-mass stars that have formed inside this nebula, casting their starlight into that gas cloud and illuminating it. But you also have a substantial amount of red light here. I mean, you get it everywhere. This field is full of reds. And this is all hydrogen gas that is interacting with ultraviolet radiation from stars. And right in this region here, the star-forming nebula, it's all the ultraviolet radiation coming off of the stars that formed inside the nebula. And it's ionizing the gas cloud that star formation is forming from. Same thing is happening here. And though in this region here, it's not so much star formation you're seeing, this is more so stars that reside in this area of the Scutum Centaurus arm have a substantial amount of hydrogen gas or a nebula moving through the region, and the starlight and the ultraviolet light is ionizing that hydrogen gas. And this is called an emissions nebula, those reds that we see. And the third type of nebula that we have all over the place here is these dark regions that you see in here, right over in here, right across the center, over in here, all this over in here. I mean, these are all dark nebulae coming across the center of the Trifid. And dark nebulae are, like we said earlier, they're parts of the nebula that are closer to us, closer to Earth. So the side that we see isn't interacting with starlight, it's not interacting with ultraviolet radiation, and it just appears dark from our point of view. If we were to look at the other side of it, you would see interactivity with a lot of it, not all of it. Now, a lot of this over here, on the other side of it, we may not see interaction at all. This just may be a cold hydrogen cloud of gas in this part of the galaxy. Now, let's zoom in here on the Trifid Nebula. So the Trifid Nebula right here, this is a region of star formation. The Trifid Nebula is similar to the Orion Nebula or to the Lagoon Nebula that we were looking at before. You're looking at a region of star formation, but we're looking at it on edge. So we don't see it You don't see necessarily how wide it is, because it's not necessarily completely round. It definitely has a wider axis, and then it has a much more narrow axis. And that's where we're kind of looking at it from. And though you don't see too many of the stars inside of it, you got a little bit going on right here. But in this case, most of the stars are buried. In the background here, you have a lot of that reflection nebula from all the stars inside of it. And right here, you have a lot of the emissions nebula from some of the higher mass stars. And this dark nebula that cuts right across the center. And the reason it's called the Trifid Nebula is because you have these 3 different types of nebula, all in a very close proximity to each other. But jumping back to the Messier 8 field, this nebula has something really excellent happening. So when we think about, evolution, everything is technically in a transitionary state. Nothing is static. But this object here is actually in between 2 marked states. So when you have a star-forming nebulae, all of that gas that goes to star formation, as those stars start to form, they start to blow away a lot of that gas. And only about 10% of the gas cloud actually goes to star formation. When the stars start blowing the gas away, eventually that young cluster of new formed stars called an open star cluster will emerge. And that's what's happening right here. So we are actually observing this nebulae at a point in its evolution where that young star cluster is starting to emerge from the gas cloud, which signals to us that star formation in this nebula is coming close to an end. And what we're seeing here is largely just all the high mass stars. And I can't zoom in on too much on this image. I should put a larger image up. These stars are actually quite blue. In this image, they look more white because they're contending with the bright starlight beyond them. But being high mass stars, they're blue. And this is an object that we frequently look at Frosty Drew. Now, to your eye in the telescope, you won't see this as red and deep blues. What you would see is largely grays and subtle blues, because a part of your eye that we use to look at dim objects only sees in grayscale. But this image captures the true color image. It was captured with a color sensor in the camera. So I am going to leave you guys with a bunny with a pancake on his head.
What's that nebula's name?
This is called, when you can't answer a question or you just have nothing to say, I put the bunny with a pancake on his head up, because it's just, it fills the gap, right? So
It's funny.
We are now down to our last minute. And first I want to say thank you to Derek for all of that work he did this past couple of weeks in gathering all those galaxies. I mean, really, that was quite fantastic, Derek. And those galaxy images were spectacular. What are you using, a Bahtinov mask to do focusing?
No, well, I'm just using the diffraction spikes off of the secondary.
You see,
until
that's experience right there. I'll do it that way as well. But I see people out in the field with Bahtinov masks and all this crazy stuff they're attaching. And I'm like, if you just pay attention, you can actually do it with your diffraction spikes. So thank you, Derek. And second, I want to say thank you to all of you guys for tuning in and sticking with us every week while we offer these live broadcasts. We love doing it. This is a chance for us to kind of get out and share our knowledge with you guys and do what we love doing. I mean, what we do with Frosty Drew, we love doing it. We can't wait until we can open up again and see you guys out under the stars. We're working really hard to get there. I know it sounds like it's taking a long time and we're not posting wealths of information about what we're doing, but we are working our butts off to get open, to get you guys back out under the stars. And we're going to try to get everybody out there as fast as we can. So please check in regularly on our Facebook, which is facebook.com/Frosty Drew Observatory. On our website, frostydrew.org, and even on our Twitter, which is twitter.com/FrostyDrewOBSY. And this is where we're going to be posting information about our reopening and about how it's going to play out. So we're going to write about it when we get a plan working, and we're going to target June 5th. So Until then, thank you for tuning in. We can't wait to see you guys again. And hopefully next week, we will see you guys on site. So, good night.
Good night.
Good night.
All right, we're off.